All right, so remember, we are learning the interval of convergence. What's another name for the interval of convergence for an infinite series? The domain. Good. So it's the values of x for which the series doesn't approximate the function it represents, but is identical to. Okay. And we know that three possibilities can happen. It either is the same only at the center, which is true for all series, in which case the radius of convergence would be what? If it only converges at the center, the radius then would be 0, right? Yeah. It could converge for all real numbers, in which case the radius is infinity, right? Or it can converge for an actual value of r, which we find. Okay. So if we look at this right here, first of all, it's a power series because it has an x, right? X means power series. And I don't know what function this thing represents, but I can call it, big F if you want. So if you get in the habit of giving all of your series names, that's a good habit to get into. Now, typically we use the ratio test to find the interval of convergence or the radius of convergence. But what do you notice about about this guy? Does he kind of resemble another series that we studied in 9.1? It looks a lot like geometric, right? So we can actually, if we recognize this as a geometric series, we can actually answer the question much more expediently, because with the ratio test, remember, we really only find the radius of convergence by getting it into this format, right? X minus the center less than r. And then I would have to come up with a possible interval and then test the endpoints individually. Okay. But if I recognize it as a geometric series, I know then that it's only going to converge strictly when the radius is, or when r, the ratio, I'm sorry, has a magnitude that's less than 1. So we could go ahead and say then that the absolute value of r, which is the absolute value of x thirds, has to be strictly less than 1. Would that be correct? Yeah. And now to get it into this format, x minus the center less than r, what is the center of this Taylor series or what's that? The center? It's 0, right? Because if it weren't 0, you would see like x minus 5 or something, right? And that would be the centers at 5, or you would see like x plus 7, and that means the center's at -7. But if you don't see x plus or minus something, the center's at 0. So for our center, it's at 0. So we're trying to get it into x minus 0 is less than r. Well, we can actually take the absolute value of 3 out and then multiply both sides by 3. And we get 1 times 3 is 3. So there it is. The center is 0. The radius of convergence is 3. And what would the interval of convergence be? Well, it would be the center 0 minus 3 to get -3, and then 0 plus the radius 3 to get +3. Now, again, normally we would have to test the endpoints, but do we really need to test the endpoints here? We know it has to be strictly less than 1, so the endpoints aren't going to work. So it's a big time saver. Now, this one would be a real quick one to test the endpoints. It's not nearly as elaborate as the other one. If you plug in a -3 for x, you get -3 over -3, which is -1 to the n, which is an alternator. And if you plug in a +3, you get 1 to the n, which is 1. Both of those would diverge by the nth term test. So you know that the interval of convergence is strictly -3 to 3. Okay. So be on the lookout for geometric series. By the way, let's check a value that's between -3 and 3, like 2, right? If x were 2, you get 2/3 to the n. Boom, convergent geometric series. Okay. So be on the lookout for geometric series. All right, let's jump down to example C, where we can get back to some really fun type ones with the ratio test. Yay. Who said that? Oh, you, okay, that sounded I didn't recognize you. Yeah, that sounded feminine. Yeah. Now I'm gonna. Yeah. All right. I added a page. I thought I added a page. Yeah, there it is. So I'm going to come down here and add this image right here so we have plenty of room. All right, so let's look at part C here. First of all, power series, how do we know? Got an X in it, okay? Notice that series has a variable of n, but because it has another variable x, it's a power series. What's the center? 0, right? The center again is 0. So this is technically not a Taylor series at 0, which it is, but it's also a Maclaurin power series. Yeah. And is it an alternating series? Yeah, yeah. So whether you recognize it as a geometric or you're going to use the ratio test, both of those are tests for absolute convergence. So we don't have to concern ourselves with the alternator, -1 to the n. So let's go ahead and say by the ratio test. And you do want to state that by the ratio test, we're going to take the limit as n goes to infinity. And I guess there should be another one. There we go. Of the absolute value of the n plus first term. So when I replace n with n plus 1 and distribute, I get 2n plus 2 plus 1 is 2n plus 3. All over 2n plus 2 plus 1 is 2n plus 3 factorial. Okay, so don't forget to distribute. And then divided by the given one, which will be multiplying by the reciprocal, 2n plus 1 factorial, all over x to the 2n plus 1. And again, the alternator's out of there. Now what I like about the ratio test, the fun part where we get to simplify. Let's see, the top is x to the 2n times x to the third. Oh, yeah, up here. So we get 2 times n plus 1 plus 1, right? And then you distribute, you get 2n plus 2 plus 1 is 2n plus 3. Okay with that? Yeah, I'm sorry. Yeah, you holler if I go too fast or I make a mistake, or if you're, I guess, in pain or something, right? And then we'll call the nurse. And then in the bottom, that's going to be x to the 2n times x to the 1th. So that takes care of the x's. And now, which is bigger, 2n plus 1 or 2n plus 3? 2n plus 3, right? So we'll write that recursively since it's factorial. That's 2n plus 3 times 2n plus 2 times 2n plus 1. And I can stop there because that matches the 2n plus 1 in the top. So now I could just tie that off with a factorial. And now we can start dividing things out. So kind of the fun part, right? X to the 2n's are gone. And then 2n plus 1 factorials are gone. And if you want to rewrite it, just to kind of take inventory, we're left with x cubed in the top. And on the bottom, we're left with 2n plus 3 times 2n plus 2 with an x. I'll put the x. I guess I'll put the x in the front where it was. Doesn't really matter. There's an x right there. And by the way, do one of those x's divide out? Yeah, so actually I could do that. So x cubed divided by x, that's just x squared. So let's write that as x squared. There we go. Now remember, since we're still evaluating the limit as a function of n, we're treating x like a constant all this time, yes? Yes. And so what would the limit as n go to infinity be then of a constant essentially divided by what would amount to a 4n squared? Zero. Good. Because the top is a constant. Now, if the top had like x squared, n squared, then it would be leading coefficient over leading coefficient, which would be x squared over 4. But there is no n squared up there. So a constant over a quadratic, it goes to 0. The x's are gone. Now, by the ratio test, We want to force it to converge. But guess what? Isn't 0 less than 1 then for all values of x? Yeah, 0 is less than 1 for all x in the set of real numbers. So it doesn't really matter what x is, right? If x were 5, that would be 25 squared over 4n squared. That goes to 0, which is less than 1. If x were a half, that would be 1/4 over 4, which would still be less, go to 0, right? So whenever you get a number at the end and the x's go away and it's always less than 1, we could say so, and let's come up here and give this guy a name. How about big H for Hank? He was first one here this morning. So H converges for all x in the set of real numbers. So the interval of convergence would be what? Yeah, all real numbers, but you do want to write it as an interval. If it does ask for the interval of convergence, don't just say all real numbers. Write it as an interval from negative infinity to infinity. And the radius of convergence is what? Infinity. Yeah, there we go. So this one, whatever this function or the power series is representing, it models the function 100% perfectly every single time for every single value for all values of x. Now, we don't know what that is. If you want to know what it is, you could start writing out a few of the terms and graphing it on your calculator, and you can get an idea of what the function might look like. But even if you know what it looks like, you may not be able to recognize the equation. That's something entirely different. Okay. All right. Questions on that one? All right, let's try, let's see, A, B, C. D is next. D is next. So copy that one. Come down here. Paste. All right, we want to figure out the interval of convergence. First of all, power series, yes? I spy an X. Power series. What's the center? 3. Good. This one has a center of 3. We know that this series for sure converges at 3, right? For sure. But are there other values? Well, I don't know. Let's see. By the ratio test. By the ratio test. We get the limit as n goes to infinity of the absolute value of. Replacing n with n plus 1, we get n plus 1 factorial times x minus 3 to the n plus 1. Now, because our nth term or rule of sequence is not a quotient, I can just divide by the nth term. I don't need to do state change flip. All right, and then if we simplify, let's see what we got when we simplify. What is n plus 1 factorial divided by n factorial? It's n plus 1, right? And then x minus 3 to the n plus first divided by x minus 3 to the nth. So just be x minus 3 to the first. It's all over 1. All right, now as n goes to infinity, we can treat x minus 3 like a constant. So the coefficient of n would be x minus 3. But what's happening as n goes to infinity? What's infinity times a constant? It's infinity, right? So this thing equals infinity, regardless of what x is. Is infinity less than 1? No. So instead of saying is greater than 1, I'm going to say it's not less than 1. Okay? We're trying to force it to converge. So, and we give this guy a name. Let's see, how about script letter S? Sophia was the second one here today. So S, do we say diverges for all x? It converges for what? X equals 3 only. Okay, it converges for 3 only. We can't really write that as an interval. every series converges at their center. Okay. And the radius of convergence is what? Yeah, is 0. All right. So it's real easy to say, it didn't pass the ratio test, so it never converges. No, it's not quite true. It will converge at its center. But that's it. That's it. Okay. So we did kind of the good one, which was part A on Thursday last week. That's the one where we had to test the endpoints after we found the interval. Okay. But there'll be more like that later on. Okay. All right. Questions on interval convergence and radius convergence? Ratio test. The ratio test, by the way, would have worked for this one as well. You want to do this one real quick? If you're going to use the ratio test, okay. If you want to use the ratio test, you're going to want to write it as x to the n over 3 to the n. Okay. So let's go ahead and say by the ratio test. We'll say, okay, the limit as n goes to infinity of the n plus first term would be x to the n plus first all over 3 to the n plus first, and then divided by that or multiplied by the reciprocal times 3 to the n over x to the n. And now we simplify, and we get x to the n times x to the first times 3 to the n in the top. And at the bottom, we get 3 to the n times 3 to the first times x to the n in the bottom. And then we simplify. Let's see, x to the n, 3 to the n. And what we're left with is the absolute value of x over 3, which again, if we treat x as a constant, what's a constant over 3? What's the limit of a constant? 3 is a constant too, right? There's no variable n anymore. So the limit of a constant is just a constant. So it equals that, right? There's no n variable anymore. So now we force that to be less than 1. And because the center is 0, if I multiply both sides by 3, I get x minus 0 is less than 3. So we know from that that the radius equals 3. All right. And then from there, we would say, okay, if the center is 0, I can go plus 3 to 3 for my high point, minus the radius 3 from 0 to negative 3. And now I would have a possible interval, a possible IOC of bracket parentheses negative 3 to 3 parenthesis bracket. And if you still didn't recognize it as geometric, now you'd have to test the endpoints. So let's go ahead and review that. Let's test the endpoints. So let's do the negative one first. When x is negative 3, we plug it back in way up here to the original function, the original series. We're going to get f equals sigma from n equals 0 to infinity of negative 3 to the n all over 3 to the n. Okay, and then to simplify that, we would want to separate the alternator from the magnitude. So negative 3 to the n is negative 1 to the n times 3 to the n all over 3 to the n. And then those divide out. And so what we're left with then is just n equals 0 to infinity of negative 1 to the n, which diverges by the nth term test. Because it's plus 1 minus 1 plus 1 minus 1. In other words, the limit as n goes to infinity doesn't equal 0. So we can't include the left endpoint. Hold it? Yeah, sure. And then we would test the other endpoint, x equals 3, and you'll get f equals sigma from n equals 0 to infinity of 3 to the n over 3 to the n, which that simplifies down directly as 1. Well, that's 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. that also diverges by the nth term test, which diverges by the nth term test. So we can't include 3 in the interval either. So the interval of convergence is strictly -3 to 3, and the radius, for what it's worth, is still 3. So again, if we would have recognized that quickly as the geometric series, you could answer the open interval from -3 to 3 much more quickly, because you wouldn't have to test the endpoints. Okay, because we know it has to be strictly, absolute value strictly less than 1. But nonetheless, if you don't recognize that, the ratio test still works. You test each endpoint, you still get the same result. It's just a little bit more work. Okay. Yeah, 23, 22 seconds, 19, 19, 19, 19, 19, 19, 19. 19 days, 19 hours, 19 minutes, and 19 seconds. Hank, I like how you focus on what's important. Okay. Which is why you don't want to miss Thursday's math club meeting with Ethan. That's right. All right. All right. We're now going to look at the special family of power series. Yeah. Well, we've seen this before. For a Taylor series centered at x equals c, it has the same look as the Taylor polynomials. The only difference is we have infinitely many terms instead of a finite number of terms. And therefore, we say the function equals and doesn't approximate. And if c of 0, we call it the Maclaurin series. So once again, this right here is the nth term. This is the nth term that we can always use using Taylor's rule. Right? Again, these are your coefficients, and then these are your variables. Now, whenever you write the nth term in the field like that, it's typical to put plus ... plus the nth term, and then plus ... And as long as the nth term captures the pattern, you don't have to worry if it is associated with n equals 0 or 1. But when you collapse it down into sigma notation, now you need to make sure that wherever you start it has to match with the first term, okay? In sigma notation, be sure your starting n value corresponds with the first term. Or I'll just put gives the first term. If not, just adjust it down there. Say starting at n equals 1 or at n equals 2. Or if it starts at 1, say n equals 0. You don't have to worry about that when you list it in the general field, okay? All right, so it says find a Taylor series for f of x equals e to the 5x centered at 2, give the first 4 non-zero terms and the general term. The general term means the nth term. The general term, the nth term, the rule of sequence, same thing. Now, are we going to be able to piggyback on the one that we memorized? We memorized the Taylor series for e to the x centered at 0, which was the Maclaurin series. If your center is different, you have to generate it anew, okay? We can adjust old series by multiplying by x, multiplying by a function of x. We can multiply by a constant, and we can even substitute in. But if we're changing the center, we have to redo it. So let's go ahead and review how to do that. If our center is at 2, we're going to have the function, which is also known as the 0th derivative. That's e to the 5x. And then we're going to have the 0th derivative or the function evaluated at 2. So that gives me e to the 10th. All right. Now, since we need the first 4 non-zero terms, we're going to need to go to the 4th derivative here. So the first derivative is 5e to the 5x. And then the first derivative at the center 2 would be 5e to the 10th. The second derivative at x is going to be 5 times 5, that's 25, or how about we call it 5 squared e to the 5x. Are you okay with that? And then the second derivative at the center would be 5 squared e to the 10th. The third derivative, instead of calling it 125 e to the 5x, how about 5 cubed e to the 5x? And then the third derivative at 2 would be 5 cubed e to the 10th. The reason that we're not calling it 25 and 125 for the coefficient is we're trying to write the general term. And if you can look for patterns, especially patterns that are functions of the derivative number that you're on, you can write the nth term a lot easier. And for what it's worth, the fourth derivative is going to be times another chain rule times another 5. So that's 5 to the 4th e to the 5x. And the fourth derivative at 2 is going to be 5 to the 4th e to the 10th. So here's what we're going to say. We're going to say f of x then equals e to the 5x. Do we put equals or squiggles here? We're finding a Taylor series, not polynomial. So it's equal signs. Yeah. If it was polynomial, it'd be squiggles. All right. So remember what we have down this second column. Those are just the numerators of your coefficients. So let's start by writing the first two terms like we would for the equation of a line. It's going to be the y value, which is e to the 10th, plus the slope, which is 5 e to the 10th times x minus the x value of 2. This would be your tangent line. And then after that, the pattern picks up, okay? Because now we're on the second derivative. So that's going to be 5 squared e to the 10th over 2 factorial times x minus 2 squared. There's 3 terms. And then plus 5 cubed e to the 10th over 3 factorial times x minus 2 to the 3rd. 1, 2, 3. Actually, that's four terms already, isn't it? So I win an extra derivative. If I went ahead and wrote out that next term, which would give me 5 non-zero terms, would that be okay? Yeah, as long as it's correct, it's okay. If you ever are more accurate than you need to, you're okay. But I'm going to stop right there. Okay, now I'm going to put plus dot, 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 and I need to figure out what the nth term is going to be. Well, can you figure it out? I hope so, because we kept the powers of 5, which kept coming by chain rule, chain rule, chain rule. We didn't write them as 5, 25, 125. We see that it's going to be the same as the factorial in the bottom and the exponent. So the nth term will be 5 to the nth times e to the 5n. No, e to the, it's the e to the 10th every time. My bad. It's e to the 10th every time. Your fault, my mistake. E to the 10th, e to the 10th, all over. Okay, yeah. Yeah, I know, right? Times x minus 2 to the nth, and then plus dot, dot, dot. There we go. Does that work? Yeah. And again, that captures the pattern. So I don't need to worry about when n is 1, do I get the first term? It captures the pattern. Now, if you wanted to, if this were a follow-up question that said to find the interval of convergence, in fact, let's add that on there. Find the radius of convergence. If I want to actually find the radius of the interval of convergence, I will want to collapse it down into sigma notation. So now I'm going to say from n equals something to infinity of that right there. 5 to the n, e to the 10th over n factorial times x minus 2 to the n. And here's where I need to make sure whatever value I put there generates my first term, which is e to the 10th. So what does it need to be? A 1, a 0, or something else? It needs to be a 0, right? Yeah, it needs to be a 0. Okay, we don't have to worry about that if we leave it like this. So for this problem, since it didn't originally ask us for the radius, that would have been full credit right there. But now that I have it like this, let's go ahead and find the radius of convergence. What test am I going to use for that? Ratio test. Okay, good. So by the ratio test. we're going to take the limit as n goes to infinity of, it's not an alternating series, but it is an absolute value. So 5 to the n plus 1 times e to the 10th times x minus 2 to the n plus 1. That's the same thing as having it in the numerator because it's over 1, all over n plus 1 factorial. And I'll divide it by the given, or I'll multiply by the reciprocal. So that's going to be n factorial in the top, and then 5 to the n times e to the 10th times x minus 2 to the n. If this showed up on a free response, that would be probably part B. Part A would be generate the force for non-zero terms in the general term. Part B would be find the radius of convergence. All right, working straight down, time to simplify. Build your shelf. I do notice my e to the 10th divide out. Boom, boom, that's good. And I have one more 5 in the top. I have one more x minus 2 in the top. And then I have in the bottom, n plus 1 factorial is n plus 1 times n factorial. So that's n plus 1. So if you can simplify it without having to take that extra line, that's fine. You take as many steps as you need to. How does that look to y'all? Handsome? Does it look right? I think so, right? Yeah, that looks good to me. All right, so again, we're treating x like a constant. So we have a constant on top and the bottom. Yeah, so a constant over something that goes infinitely large is approaching what? It's approaching 0, right? Which is less than 1 for all x. So what's the radius of convergence? Good. So the radius of convergence is infinity. And for what it's worth, the interval of convergence is negative infinity to infinity. The domain of this is all real numbers. Now, of course, if it converges for all real numbers, you don't have to test endpoints, right? So the interval is almost as easy as finding the radius. But if the radius were a finite number, then testing the endpoints is a little bit more arduous. So you got to read carefully. If it doesn't ask you for the interval of convergence, don't find the interval of convergence. Okay, because it's you're going to squander a bunch of time. A lot of times they just ask you for the radius. Okay, so we know then that we can use this polynomial to represent e to the 5x for all values of x in the whole wide world. Okay, not just near the center. All right, so there are 4 special Maclaurin series that you need to have memorized. E to the x, sine of x, and cosine of x. We already kind of have them memorized, but in polynomial form. What we need to do right now is look at their nth term. Okay, and then in the next section, we'll talk about 1 over 1 minus x by itself. So let's write these out. Let's do sine of x first. So sine of x now is equal to, not approximately anymore. What's the first term in sine of x? Is it 1 or is it x? X, right? Because sine is odd. So it's x and then minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So at least 3 terms is customary. Now we can put plus dot dot dot. Would the next term be negative though? Yeah. Should we put minus dot 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 or does it really matter? Plus a negative. Actually, you don't. It doesn't really matter. If you're just putting dot dot dot. If you're actually going to write down the next term, you're going to want to make sure it's minus. Okay. If you feel better putting a minus there, that's fine. But it's going to be x to the 2n plus 1 factorial all over 2n plus 1 factorial plus dot dot dot. Now again, that captures the pattern, but notice that if n is 1, I'm getting the second term instead of the first. Now there's one other thing that I just forgot to add. I need an alternator in there, don't I? Yeah, so I need that to be -1 to the n or n plus 1. Here's what we need to make sure. I need to make sure even that the same value of n is going to give me the correct sign. So notice if I plugged in an n equals 1, I'm going to get x cubed. There should be no factorial up here. I was getting crazy. There you go. X to the 2n plus 1 over 2n plus 1 factorial. When n is 1, we get x cubed over 3 factorial. That term should be negative, right? So when n is 1, I need it to be a negative. Is it negative 1 to the n then, or negative 1 to the n plus 1? That's how you off-step it by a term. Negative 1 to the n, right? Because negative 1 to the first is negative. So that's good. If I needed that term to be positive, I would just put n plus 1. So there you go. Now when I collapse it down, if you so wanted to, now it would be from n equals something to infinity of, you could also put the negative 1 to the n in the numerator if you wanted, with the x, if you didn't want it separate by itself. And now I would need to start it at what value? Could I use 1 again? No, because my first term actually is x to the first, and it's positive. I have to start it at 0. Okay. So again, in this format, your starting n, the starting n value doesn't matter. But you do have to have the sign SIGN matching up with the magnitude. For sigma, the starting n does matter. Starting n value must give the first term. All right, so what's it going to be for cosine then? Cosine of x is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus yada, 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 plus negative 1 to the n times x to the 2n over 2n quantity factorial plus dot, dot, dot. And you can check, when you plug in a 1 for n, you get x squared over 2 factorial, which is the second term. And when you plug a 1 in for negative 1 to the n, you get a negative. So that matches. But again, when I collapse it down to sigma, we have to start at 0. Right, so we're just adding one little piece then to the polynomial pattern, and that is the general term. And you're going to want to memorize those because what we'll talk about, what we're going to do with after these. And then e to the x. E to the x. That is 1 plus x squared over 2 factorial plus, I'll do one more here, x cubed over 3 factorial plus dot, 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 plus, should be x to the n over n factorial plus dot, dot, dot. This one doesn't alternate. And again, when you plug in a 1 for n, you get x over 1, which is the second term. That's fine. When you collapse it to sigma, though, you need to be aware that you can't start it at 1 because your first term is 1. You got to start it at 0. Are there ways to adjust the rule of sequence so that I can start it at 1 and still get the first term? Yeah, but it's harder to adjust the rule of sequence than it is to just start at a different value for n. All right, so those are the 3 that you need to memorize right now. Without the sigma, that's how we write the general term or the nth term. Plus dot, 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 plus nth term, plus another dot, dot, dot. Okay. All right, now why do we want to have those memorized? Because here's what we can do. We can substitute one series in for another. We can multiply or divide by a constant or a variable. We can add and subtract 2 series. And look at this. I've talked about this already. We could take the derivative of or integrate a series. That's how I showed you how we first got the cosine series, from taking the derivative of the sine. And then number 5 is the next section. Recognize it as a geometric power series. But look what happens if we differentiate or integrate a series. This is really important. When you take the derivative or the integral of a series, it doesn't change the radius of convergence, but it may change the interval. So what does that mean? That means that you need to retest your endpoints. It's only going to be smaller by at most 2 points, the endpoints. If they were included in the beginning, maybe they're not included in the end. But it could be that it's the same interval, but it won't change the radius. So it won't change anything on the interior. If you take the derivative or the integral of a series to get a new series, you recheck the endpoints, okay? All right, let's try this out on example 4. If f of x is 1 plus x squared over 2 factorial plus blah, 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 find f prime of x. Okay. Oh, by the way, I should say that these right here, these three, these also, all three of them converge for all x. Both sides have domains of all real numbers, and they perfectly represent sine, cosine, and e respectively for all real numbers. So that's kind of cool. So if you recognize this f of x, do you recognize, it's the last question, do you recognize this familiar function? Yeah, that's the Taylor series or the Maclaurin series for e to the x. So it tells us to find f prime of x. Well, let's try it. F prime of x is, the derivative of 1 is 0, the derivative of x is 1. This becomes 2x to the first over 2 factorial plus 3x squared over 3 factorial plus dot, 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 plus n times x to the n minus 1 all over n minus 1 factorial plus dot, dot, dot. That's another nice advantage to having the nth term there before you take the derivative. You can take the derivative of the nth term to get the pattern of what the derivative will be. Okay, now let's simplify. F prime of x is 1 plus, that becomes x over 1 factorial, or just x, plus 3 over 3 factorial is 2 factorial, so x squared over 2 factorial. Now here's where we have to be careful. What if it said find, and right here I should probably add this, the first 4 non-zero terms and the general term. Could I stop right there and just say plus dot, dot, dot? I'd have to add another term because, yeah, I started with 4 non-zero terms, but the first one went to 0. Is that going to be a problem? No, you can either come back up here and add the next one, x to the 4th over 4 factorial, and take its derivative, or you could say, oh, I recognize the intrinsic pattern in the derivative, and I know the next one will be x cubed over 3 factorial. Okay, and then we'll say plus dot, 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 plus n times x to the n minus 1 over n minus 1 factorial. Plus dot, dot, dot. Yeah. Now, could I leave the nth term like that? I could, right? But I could also simplify n over n minus 1 factorial to be just what? I'm sorry, this should be, this should still be n factorial down here. I was taking the derivative with respect to x. I'm glad I did that. It didn't simplify, right? What does n over n factorial simplify to? It simplifies to 1 over n minus 1 factorial. But hey, isn't that just capturing the same pattern as x to the n over n factorial? Yeah. So which of these general terms is correct? All three of them. As long as they capture the pattern, you're good. What's different is when we collapse it down, right? This one would be x to the n minus 1 over n minus 1 factorial. This one, if we simplify, would be x to the n over n factorial. Both of them start with n equals something to infinity. But in order to capture the first term of 1, this one needs to start at 1, and this one needs to start at 0. See that? But it's the same pattern. It's the exact same pattern. If it asks you to write the first 4 non-zero terms and the general term, is there any incentive to simplify the general term to get your credit? Probably not. So I would have probably left it like this. But if you have to use it, I would probably simplify it down to either the second or the third one. Okay. Now, do we really need to test the endpoints again here? I just took the derivative. No, because I recognize it as e to the x, I know it's going to converge for all real numbers, so I don't have to test the endpoints. But the endpoints could have changed. Now, what's f prime of 0? Plug it in, and you get 1 plus 0 plus 0 plus 0 down the line, which is 1. Well, is that the same as e to the 0? Yeah. Okay. So there you go. We'll pick up with example 5 tomorrow. 5, 6. We should be able to finish this tomorrow. And then I will probably, well, we'll talk tomorrow about what we're doing Thursday, okay? Y'all have a good day. Memorize, memorize, memorize.